All right. Welcome, everyone, to the January 30th OpenJ9 community call. This week, we're going to kick things off with a lightning talk from Vijay on escape analysis in OpenJ9. Before we jump right into that, I'd like to give anybody a chance to raise any other questions they may have, or any other topics they'd like to raise or add to the agenda for today. And it's okay if there's none at this exact minute. We can add them in as we get to the different parts. If there's time today, I'd also like to run a bit of a retrospective on the 0.12 release. And that retrospective may move to the next call as well. So at this point, Vijay, I'm going to hand control over to you if you want to start sharing and jump right into your lightning talk.
Yeah, I think yeah, you have to stop sharing before I can do it. So I'll get in now. Okay, are you guys able to see it?
Yes.
Okay, great. I'm Vijay Sundaresan. I'm working on OpenJ9 performance, and today I'm going to be talking about escape analysis in OpenJ9. There's been some recent work done in this optimization that I wanted to come back to this forum and do another lightning talk on in the future, but I figured I would do a more basic what is escape analysis lightning talk first. So this is that kind of basics of escape analysis. So what is it? It's basically a JIT compiler optimization that has a very straightforward goal. It converts allocations done on the Java heap to instead be done on the Java stack. On the Java heap, if you do a new in Java, your allocation goes on the heap. And the goal of this optimization is to remove that allocation from the heap and allocate it as part of the stack frame that is built up along with local variables and parameters and other things that are on the stack. So why would this optimization want to do this? Getting rid of objects from the heap reduces pressure on the garbage collector. If there are fewer objects in the heap, the GC overhead is lesser. It doesn't need to work as hard. Keeping things on the Java stack helps with object locality. Local variables on the stack are accessed a lot by the Java code in most methods. And as such, you would expect the stack to be in the machine's cache. So having object residing there as well increases its chance of being in the cache as opposed to existing at some random spot on the heap somewhere. And as I'll talk about a bit later, doing escape analysis also enables other optimizations that just reduce path length, so lead to better instruction sequences, shorter instruction sequences in many cases. So there are several advantages to doing escape analysis in the JIT compiler. Okay, so I thought I'd show some common use cases where escape analysis actually kicks in and does its job. And I'm going to show three Java use cases that hopefully drive home the opportunities as well as the scenarios in which escape analysis gets involved. So use case number one is string builders that are used for appending strings. So anytime, so that's show a piece of Java code here. Have an int and two strings, and you're just appending them to do a print. Behind the scenes, what comes out in the bytecodes is that there's a string builder object created in the bytecodes, and then that string builder object is used to do the concatenation. So you're calling the append method on the string builder, oftentimes with these arguments, and creating a larger string out of that, and that final larger string is created by calling toString on the string builder. So that happens transparently. Javac does that for you. And the lifetime of that string builder object generally is basically limited to the code that is doing the append. So it gets created just before the appending starts. And once the concatenated string has been created, it kind of ends, the lifetime ends at that point, and that object is basically ready for garbage collection. So as you can see, it's very limited scope that the object is created for. It's not really even visible to the rest of the Java program in this case. So it's very, it's basically transparent to the rest of the program. It just springs into existence for this short duration and goes away. And the key part is that its lifetime is within the method's invocation, the method that contains this code. You're not going to have that string builder survive past that method invocation. The next use case, again, a very common one, to use iterators to walk over collections. So let's say you have a list and you call iterator on it, and then you're just standard iterating through that list by calling has next and next. What happens there again is that the iterator is basically only used inside the loop, and it's a convenience for iterating over the list. It doesn't hold any great state for the rest of the program on its own. It just offers these convenient methods, has next and next. So the lifetime of iterator objects is also very short-lived. It's just for the duration of the loop, pretty much. And then the iterator, in most cases, is not used subsequently. So once again, the lifetime is limited to just the method invocation. In fact, as I said, it's even narrower than that, just the loop, typically. And the third use case is one which involves boxed primitives and operations on those. So if you see this Java code, you have a double variable f inside the loop. That double variable is actually an object because of the capital D there. It's not a primitive double, it's an object double. And as you can see in the loop, that object is used to calculate another result, which is also a double. So there's arithmetic going on inside this loop, double arithmetic. And the way this is handled by Javac is, again, by generating temporary double objects to hold those intermediate values. So when one is doing result plus 1, that gets held in an intermediate double, which then gets used to do the division with f, and so on. So again, these are objects that are not even visible in the Java code, but are generated behind the scenes. And once again, the lifetime of these double objects is very short. It's typically just one iteration of the loop until you use it to do certain calculations, and then once the end result that survives that loop iteration is calculated, these objects have no value at that point. So, again, and the point that I bolded there is that its lifetime is within that method invocation again. So that's the key. If you have these kinds of short-lived objects, and I gave just 3 examples, that people could write arbitrary Java code really that has short-lived objects that only live for one method's invocation. That point is key. So let's move on to the next slide and see exactly how escape analysis, or what it is that it means when we say that an object does not escape. Basically means 2 things: that the object does not get escape to another thread, and also that it does not outlive this method invocation. Note that if you return an object that outlives the method invocation, but does not actually escape to another thread. To escape to another thread, you would have to store an object to some kind of global variable, like a static or a field or an array element or something like that. But these are the 2 rules essentially that escape analysis is trying to enforce, and it's trying to do its analysis subject to these rules. It's trying to find allocations that do not escape to another thread and do not outlive this method invocation. And it does this by doing a compile time analysis of the intermediate language trees in OpenJ9's JIT compiler. And it checks basically at a high level, the analysis just checks how new allocations are used and passed around. And if an escape is detected, then it says, I cannot do stack allocation on this object. Something has happened here that makes the object escape. So I cannot allocate it on this in this method's frame because its lifetime is longer than this method invocation. And in order to do this analysis, it uses a lot of the machinery that comes from the Eclipse OMR project that OpenJ9 uses and consumes. The infrastructure there is for building use defs and calculating which users correspond to which stores, which loads correspond to which stores, and another analysis called value numbering, as well as speaking into method calls, so looking inside called methods to see what's in them. These are all sort of infrastructure offered up by the Eclipse OMR code base. So at its core, how do we decide if we can stack allocate a given object? As I said, we use the usedef info and value number info to collect all the related value numbers that may represent a given object. So we're basically saying where all can this object reach in the code. And once we've looked at each related value number to see how it's used, we can check if it was used in a way that can lead to an escape. So what can cause an escape? Well, I listed the different events that lead to an escape at the bottom of the slide. So if you store the object out to a reference field or an array element or a static, as I said, that's an escape because now it's no longer tied to this method invocation. It's available or accessible from a global and can be accessed after this method returns as well. If you return the object itself or you throw it, that constitutes an escape. If you store it to an auto, local variable basically, inside a method that we're peeking, that makes us conservatively say that the object has escaped because we have very rudimentary analysis on how we analyze the peaked methods. We don't really do anything complicated there. If we lose track of a method, of an object that has gone into a called method, if it gets stored out to another local variable, we just throw our hands up and say, we don't know what's going on here, so conservatively it cannot be stack allocated. And if it's passed as an argument to certain kinds of method calls, I'll deal with method calls separately a bit later. Okay, so moving on, what kinds of escape analysis can we do in OpenJ9? So I said that we're allocating objects on the stack. That's fundamentally the transformation that's happening here. But there are two variants of that. One is called contiguous stack allocation, and the other is called discontiguous stack allocation. So contiguous stack allocation, basically you allocate the object as is, so in its original shape, with a header and all its fields laid out exactly as it would have been, except that you allocate it on the stack. So it still looks like this, still looks the same as it would have been if it had gone on the heap, but it just resides on the stack. And one advantage of this is that if, or one optimization that you can do in this case is you can eliminate synchronizations on the object because you've proven that it does not escape to any other thread. The more powerful form of stack allocation, though, is discontiguous stack allocation. In this case, the object shape is not retained. In fact, there is no object. Stop thinking of it in terms of an object. The object is simply exploded into individual autos on the stack. So each field becomes its own local variable on the stack. And those local variables can be optimized as any other local variables that were there in the method anyway. Those local variables can be mapped independently of each other They no longer need to be next to each other. They no longer need to be in a given order. Basically, the object is gone completely, and only its constituent fields or the relevant fields are there, and they're stored as local variables. This is very powerful because the OpenJ9 JIT has a rich suite of optimizations that optimize local variables quite nicely. So all those optimizations engage when a discontiguous allocation happens. As I said, discontiguous allocation is more difficult to do, though. It requires more stringent criteria for it to succeed or for it to happen. So this slide kind of talks about the conditions in which we may be forced to go discontiguous instead of contiguous. And I list some examples of things to give you a feel just for what could lead to a contiguous allocation. So here, the first little snippet of code that I show there is a control flow. So 4 can emerge. So you have a condition being checked and an allocation happening on one side of the condition, and on the other side of the condition, you're just picking up some other arbitrary value. After that, you go and access myvar.f, which could be pointing at your allocation, but could also be pointing at some other object entirely. So in this case, you can't just go and blow up the object into its constituent fields. You can't do a discontiguous allocation because you have no idea what happens on the other side of this if. So the static variable could be a heap object, and so you can't really use a local variable to access myvar.f. So you need to keep the object whole in order to have a consistent access scheme at that field. In order to access the field, you need an object, and so you need to keep the object whole so that you can generate a nice, simple field access at that point. So in this case, the allocation becomes contiguous. Object is still there, but it's just sitting on the stack. Other things that could cause an object to become or stay contiguous is if the object is passed out to a call, and we cannot inline that call in the JIT. If the object is an array and we do not know the index of the array element being accessed, these are all cases in which we don't have a good idea how to just blow up the object into its individual fields. We need the object as a whole, and so we do contiguous allocation in this case. You can't pass out an object to a call if you blew it up into its individual fields, not without changing the linkage dramatically. There's talk of doing something like that in a very restricted scenario, looking ahead at Valhalla and value types and so on. But in general, we don't do that. If you pass an object out, we need an object, and it needs to look kind of quote unquote normal. We're getting to the end of this talk. Calls are special in escape analysis. We need to treat them, especially if you're calling out to another method. The most ideal case is if the object is being passed out as an argument to that method. The most ideal case is you just go and inline that call. And now you have code in the method, and you can just access, you can see everything, you can analyze it to your heart's content. If you cannot inline it, then the next best thing that we do is we go and start peeking into it, just look at the IL in there. But the disadvantage of peeking versus inlining is that if you peek, you don't do all the elaborate analysis that we would do if the method had been inlined. Peeking is very rudimentary. It just kind of looks for some very common escape points and things like that. But as soon as you have complications, as soon as you assign an argument to a local variable, for example, the analysis becomes very conservative and no longer tracks it accurately as it would if we had inlined it. So peeking is less ideal, but we do it, and it does succeed in some simple cases. If we cannot inline or peek a method call, then if the call is in a cold block, we kind of can take a different track and ignore the call altogether and treat it as a cold escape point and compensate accordingly. And the last slide actually talks a bit about that. So what are cold escape points and how are they handled? Basically, if a cold escape point is a place where you have to conservatively assume that the object escapes, but it's a cold path. And you can choose to handle this differently on the assumption that extra overhead on those cold paths is worth the cost for optimizing hot paths. So when you take that cold path, what the JIT does is it inserts code on those cold paths to say, okay, you're about to go into this cold path. You may be escaping in this code. So I am going to take the stack allocated object and heapify it within quotes. And heapification means it will create an object in the heap, copy over the contents of the stack allocated object into that newly allocated heap object, and pass out the heap object to the call. At that point, it also goes and updates all the references that used to point at the stack allocated object to instead point to the heap allocated object. And from then on, the object is basically living on the heap. So the assumption, obviously, this is not a good idea to do a stack allocation and then to heapify it very frequently, but this only kicks in on cold paths. So you're not expected to do this, but the code to do heapification is there, it's generated in case you take that cold path and in case you need to be conservatively correct. So that's pretty much it. One common case of cold escapes is guarded virtual calls. So virtual calls in Java are present all over the place. The way that JIT optimizes those is by inserting a guard test before the call and generating a direct call to them in cases when it can prove the method that's being called. But it still needs to leave the virtual call around in case a future class loading event, a future dynamically loaded class comes in and requires you to take the other path. So those virtual calls that are left there can sometimes be can sometimes lead to escapes if the object is being passed out as an argument to that. And it would be a shame if you were not able to somehow handle that. Objects would appear to be going out through calls that you cannot peek and cannot inline all the time in those cases. So again, the cold block heapification technique really helps those guarded virtual calls, as we call them, on the JIT. So I'll stop there and hope that was a good overview of what we do in the escape analysis opt. And if there are any questions, please go ahead.
Thanks, Vijay. One question for you: does the size of the object affect our willingness to do escape analysis?
Yes. So that's a good question. We need to know the size of the object first of all. So a variable length array is not eligible, and it has to be under a certain limit. I believe that limit is in the 500 byte range. But there's a budget as such for the entire compile as well. You can't just blow up the stack size arbitrarily just because you found opportunities.
Are there any other questions for Vijay at this point?
Okay, in that case, I'll stop sharing, and thank you very much for your time.
Thanks, Vijay.
No problem.
Then I will pull the agenda back up as well. All right. So Vijay will hopefully get the recording of this up on the OpenJ9 YouTube channel this week, and then we'll edit the lightning talk out so there's a shorter video there for anybody who needs to just watch the shorter video.
Okay, great. Thanks.
That may take a little bit longer to get put up, but
yeah, no worries.
All right. Looking at the time that we have left for this talk, I'm going to pull up the user-raised issues and just take a look for anything that new that's come in. I see we have an investigation into a performance delta that was brought to our awareness on Twitter. So we've just started looking into that. There's a question around the J-Link size. The JRE we produce out of that is bigger than the hotspot one. This is the on-disk size, not the in-memory size. So we'll need to take a look at that as well. There's an issue around files with umlauts not working. We've targeted that to the 0.13 release to make sure we can get that into the next release that we get out. And then looking at the other things that are new, the JVM and queue operation stubbed. This is usually found when we find people running hotspots attach API on OpenJ9. So there's some suggestions on how to make this more obvious to people that what they need to be running is the OpenJ9 version of attach. And then in terms of things that are still or recently being updated, this image files not displayed properly is actually due to a bug in OpenJDK. There's a mismatch in the signatures, but we've also found ways to potentially work around this in OpenJ9 as well. So there should be a pull request for that shortly. I believe we've talked about the other user-raised issues on previous calls. So unless there's some questions or concerns about any of these, I'd like to jump back to the agenda.
Did we fix the bug in the extension code?
It's a good question. We raised an issue with OpenJDK. I believe there's a patch for the head repo. I'm not sure if it's been fixed in the extensions yet or if we're waiting for the backport.
Oh, too late now. It would have been nice maybe to fix it for the 0.12 release.
Agreed. Can dig into that as well. Let's jump back to the agenda then. And then in terms of the 0.12 release, the GA builds were created as of this morning, I believe. If someone can confirm that.
Sorry, on mute there. So the builds that adopt with the latest 0.12 OpenJ9 code are still running at adopt. So there's quite a lot of pipeline activity building and testing as we speak.
All right, so we expect those to be out to complete today, or will that take till tomorrow to run through?
It's probably take tomorrow. I'm just looking at them. There's still a few waiting for machines at all to run, so I suspect they might be finishing in the dead of night, in which case it'll be the morning when we check them all out. Now, I think because the builds are being issued with a release tag in their build pipelines, they will be published as releases anyway, because that's kind of the way the system works, regardless of whether we verify the results. So let's hope we don't have to unrelease them, but they will be going up when those jobs finish.
But the functional testing and the system testing is already run at OpenJ9, so I'm not sure it really needed to be rerun at adopt.
Well, there's the OpenJDK regression tests running there. Don't believe you run them at OpenJ9.
We don't. Also not sure. They've never passed completely, so I'm not sure we would do anything, even if something failed.
Mm-hmm.
We've already declared GA, so I don't think we can take that back.
Mm-hmm.
All right, so thank you to everybody who's been involved in getting these builds pushed through. I know that this has been a longer release process than we would have liked in some ways. With our original target date of January 23rd, we're coming in not quite 10 days late. So what I'd like to do is to run a retrospective on this release, but given that we're sort of 7 minutes left in our time frame on Zoom, we may need to defer that until either the next meeting or the one after.
One thing we can think about is a code split feature complete date for the next release. I don't know if we have time to discuss that part, but I'm thinking March 4th.
So yeah, if we look at it from the point of view of a user wanting to consume the latest quarterly updates for security fixes, we really need to have the OpenJ9 code, whatever we decide it should be, ready on OpenJDK release day. I feel, and I think we're missing that currently.
So the next release is actually Java 12, so there's no security updates in the next release.
Mm-hmm.
So the Java 12 code should be pretty much done at OpenJDK now, pending maybe a couple of bug fixes, but it tends to get settled pretty early.
So Pete, you're suggesting we should branch March the 4th?
Or earlier. I don't know if people think it should be earlier than March 4th. I'm a bit concerned about being able to get all the Java 12 work done in time. In which case, if we do branch March 4th, we'll have to double deliver everything after that date. But maybe we need that time. That gives us a little over 2 weeks to stabilize, which may not be enough.
Yeah, we may want to target that earlier.
February 20.
Is everything that's in the milestone for 13 still planned? Or are you still moving things around?
So I'm not planning to move anything right now, but anything that doesn't make the date that we're talking about right now and isn't related to Java 12 will just be moved to 14. So what we need are the Java 12. We need to ship Java 12. So anything related to that, including crashes or test failures, anything else that's a feature can just move out.
I think I saw concurrent scavenge on P. Is it P or Z, one or the other? In
so
30.
I mean, if they can get it done by the date that we're talking about, by February 28th, that's fine. It can be there in the Java 12 release, but we're only releasing Java 12. There'll be no Java 8 build, except for in the nightlies.
Yeah, I think the earlier branch is going to be key to help us close out any last-minute defects. We found that we've had some that have sort of dragged on and pushed our release. So this will be a better way to stabilize early.
28th. That's the Thursday instead of the Monday. I would do like the 25th if we're going to have it earlier than the 4th.
Seems reasonable to me. It does really give us a compressed timeline to finish any Java 12 work. But
well, the Java 12 work can still continue after that date. Just means it has to be double delivered. So we'll do a code split, and we won't refresh that split after the 25th from the main line. Anything that still needs to get in will have to be double delivered.
that seems reasonable. Let's pick our stake in the sand and say, here's where we are, and anything that doesn't make that, we need to look very hard at whether it needs to be in 12 at all or in 13. Someday our numbers are going to work better in JDK 12, in the OpenJ9 release of JDK 12. All right. In terms of time, we're down to the last sort of 2.5 minutes. Is there anything else anybody wants to bring up? All right, then thank you everybody for joining the call this week. And we will meet again next week. And thank you, Vijay, for the lightning talk.
No problem. Bye.